Hi, my name is Sanjar. I'm software engineer at ResearchGate, and today I will talk about our use case, which involves windowless joins of the streams. ResearchGate is a social network for scientists, and even though the internet evolved from the researchers, nowadays research is not mainly done online, and ResearchGate tries to fix that by bringing the process of doing research and all of the scientific content online. And to do this, we have many features such as profiles of a profile of a researcher, publications and contributions, question answers, so researchers can effortlessly share negative results, positive results, and ask questions about, let's say, some specific equipment which would be very hard to learn it the hard way. And this is about implementing one feature for the profile page where we would have something like research timeline. It will look something like this. We have contributions of a researcher in a chronological order, and these contributions may be publications, comments, articles, questions, answers, and it's kind of spread across the system, and we have to give it in a chronological order, and it should be possible to paginate, filter, which might make online queries against data sources very hard. So we can filter on the metadata from different sources, and there is even multiple call to action, like people can add new research, and this should be immediately reflected in the researcher's timeline. And some buttons are not visible. You can actually delete some of those, and when they are deleted from the source of truth, it should be immediately gone from this page. So it's pretty strict requirements for the latency. And so to get all of this data, we have to look at many sources. And if we take only one card, like this is one type of card, and this is about publication. Here we see that publication has a title, dates, and authors, some numbers with read, citation, statistics, and if it's being followed or not. And the topic of this talk is about just the simplest part of the join, where we want to, for the publication, we want to know the accounts who authored that publication, and if we solve one join in a stream, we can convert any problem to that join and solve it. But first, about our current technical state of things, we have lots of services which own the data, and the data can be stored in diverse types of systems, like caches, Mongo, Solr, search indexes, HBase. There is even SQL. So data is really, like, we have lots of data, and it's not stored in a single unified manner. The unifying thing is serviceware, which kind of encapsulates the data. And on the backside, we have the big data pipeline where we analyze all of this data, and we have periodical snapshots. We import it to Hadoop cluster and do expensive calculations there, and then export it back to the services. And to solve our join problem, first I have to talk about data model, and it's kind of, on one side we have a publication, and on the other side we have a registered account. And the publication can be authored by multiple authors. And these are kind of names. It's virtual entities which have metadata of its own, like affiliations and stuff. And account registered user can claim multiple authors. So the author is kind of linking entity. There is one more hop to get from account to all of his publications. And in a hypothetical SQL, if we have such advanced thing which works across the databases, we would model it something like this. We have accounts table with primary key of account, and we have array of authors which that account claimed. And on the other side, we have publications with IDs and array of authors for that publication. And we would just simply join that. We would join accounts with publications on a condition where any claimed author matches any author of publication, and that way we would get a pair of account and his publications. And we would just create a materialized view of it, and with like refresh fast on commit, so we would immediately see the materialized view reflect the changes for the source table changes, and we would do it incrementally without any penalty. But reality is that we don't have such SQL and such storages. It's just spread across systems. So the challenges here to build it is, data is distributed and diverse. Even if we just want to get the data and to some hash map and do a join, it doesn't fit in a machine. And if something goes wrong in the middle of the process, again, restarting that thing might take hours or days. So we need fault tolerance. And we want to be able to deploy changes fast, and we want actually zero downtime deployments, because we have call to action buttons, so user clicks and expects the change to be reflected in the next request to the backend. And so we want zero downtime and fast deployments. It should be effortless to just modify your join and with one command deploy and see the results. And we want so it makes sense for A/B testing, for experiments, to have different join conditions to benchmark against. And we want, of course, join result to be immediately available. And of course, we want the join to be correct. So we don't want some phantom data or some inaccurate stuff. Like we are dealing with profile of the researcher, and that should reflect the current source of truth. So the diverse part is actually solved with very simple idea called change data capture, and maybe some people call it change log streams. And the idea is simple. It starts like, in the beginning you usually have microservice which wraps some database, and soon you need some other representation of the record in the database, and you like cache, and you just write it during request to the cache. Then you might need another representation, like in some search indexes, and then another in some file system, and it gets complicated and unpredictable. There are too many things which can fail, and change data capture tries to solve this problem in a simple way. So instead of synchronizing everything in the application, whenever something happens in the database, through some hooks or logical replication, we just extract the change and write it to the log. And we write it not incremental change, but the replacement value. And this log is, I think, pretty common to use Kafka nowadays. And so in the log, we can see key and the value, and key is primary key of the record in the database, and the value is the full payload of the record from the source of truth. And as new changes happen, we just extract it and append in Kafka terms, to the head of the queue. And this is a special value null. I'm not sure it's that recognizable, but yeah, this is a null value, and in Kafka, delete is represented with the key and the null value, and it signals the Kafka to collect away that record after some time. So it's the native value of the delete in Kafka. As time goes by, we just append to the log, and this Kafka has to be configured in log compaction mode to conform to this change data capture model. And so this topic is not just topic with time retention, but special retention per key. And we will have every record in that topic as time goes by. And then we can solve the caching, or like cache can maintain its own offset and scan through the log and be kept up to date. The same for other representations like search, HBase, HDFS. So this gives us pretty good thing that this solves the diverse data problem for us. We can abstract away on a changed data capture stream, and then we can convert the problem to, like, for any NoSQL or SQL or any database, we have changed data capture stream. And now the problem is reduced to joining full Kafka topics and output, in the end, again, change data capture stream, which conforms to that semantics. And then we can solve the materialization problem. And this way we can join any data and materialize that join view in any data store. So we decided to try Flink for the streaming join. And in the Flink terms, the job will look something like the simplistic version will look something like this. We have account stream, and we have publication stream, and we have to join it. And for this, we use coflat map because, Flink joins. It's kind of hard to do it with Flink join because of the evictors, and we have to resort to coflat map, which is more generic operator. And so we key the stream by the join key, in our case author. So for any author, on the one hand we want to have account, on the other hand we want to have publication, and when this is full we fire the join result. And we just key the operator by join key author. Then we route all of the accounts to the corresponding authors, publications to corresponding authors, and when it's full, we fire a join result in the output stream. The code actually fits on a screen. It's a simplistic version. We get two Kafka topics. We connect these two topics, and this way we will get two callbacks, one for, I'm not sure this is visible. We get two callbacks, one for one side and another for other topic, and we key those two streams, so the data of the author are in the same task node of the Flink. And this is how we initialize state. This is simplified version. I use value state here, but for the many-to-many cardinality, we have to use list state, but then it wouldn't fit the screen. And whenever we receive some data, we update the corresponding side, left or right, like author of account of the author, or publication of the author. And when our state is full, we just collect the join result. And the data flow will look something like this. On the table-shaped things, I have the Kafka topics, and the keys are account IDs, and the values are authors, which are claimed by those accounts. And in this case, we see a value, Alice claims author 2. The data goes to the key of author 2. We update the left side. Then we see new account, claims author 1. Data goes to another task node. We again update the left side. So we have a publication authored by author 1. Data goes to that task node. And we have full kind of window, and we just fire that. We collect the join result, and have it in the output. And actually, this does what we want. Bob has a publication, paper 1, and yeah, we have author on the left side, 1, so the join worked. Let's revisit the challenges. This one is obviously solved by the change data capture. Flink is not involved there. And that the data set doesn't fit in memory on a single machine. We run on a Flink cluster. We can set parallelism as we like and use as many nodes as we want, so the data would fit. Fault tolerance we get from Flink checkpoints. And if something goes wrong, we just have to restore from checkpoint, which takes seconds, maybe in the worst case. And we want to deploy change fast. This one is, Flink has this save points thing, which is very powerful primitive. And we can build sophisticated deployment scenarios on top of save points. We have multiple versions. We have 0 downtime, and maybe it will even, it also simplifies supervision of the jobs. And we also, because of the streaming, we have up-to-date, near real-time join result. But the correctness of the join is still, we just have one simple case. It kind of works. But what if we have a delete? Let's say paper 1 is deleted, and we have to delete it from the task node state, author 1, and we have to either delete it from Kafka topic, which is impossible, or we have to issue compensating delete for that key. But when we see that record, we can't key that record because from Kafka we have that paper 1 is deleted, but I don't know which author was authoring that paper. So to solve that problem, we have to know previous value of that key, which essentially requires us to change the job graph. When we receive from the stream, we have to store previous value. So for every stream we want, we have to have all the previous values for that stream. So we can properly route that delete to the author 1 task, and then it can issue the delete. So we want, in the end, something like this. In the K1 is deleted. But let's say we routed the delete to author 1. Now we have to issue key 1 now. And how in the task node I can know the key of the Kafka record in the output. And the obvious choice here is use natural IDs. And any business case can come up with its like natural ID, which makes sense. So in our case, it's a Bob paper 1, which means that one account can't claim one publication more than once. So one account authors publication once. And this is the natural ID here, which will solve the delete key problem. So let's say deletes are solved and we receive an update. So paper 1 has changed. Now we think its author is author 2. We route it to another key. The key is full. The task node is full. We fire a join result. But now we have this strange state where two states think that they authored paper 1. But the truth is that Alice authored paper 1. So we have to somehow fix the state on the here. We have to delete it. And the obvious choice is to issue 2 commands, delete and upsert one to old one and one to new author. Let's say we have different state, like paper 1 is claimed by 2 authors, like they are Alice and Bob are co-authors, and yeah, we have an array there. This is the correct state in the join operator. And Bob's account gets deleted. We have to delete this key. We can handle deletes now. Everything is fine. Like we propagate delete, we fix the join result. And we now think that Alice authors paper 1. Then Alice claims the author, which was claimed by Bob before. So we see a new value, and so we have to first issue a delete to the old author of the Alice. So we send delete there, we send upsert there. This might be handled by different task nodes in the Flink. And one of them will issue a delete and other one will issue an update, and the natural ID will say Alice paper 1 gets deleted, Alice paper 1 gets inserted. And depending how lucky we are, we can either end up with correct state, or we can end up with such state where nobody claims paper 1 because the order of insert and delete was not preserved. So the collect order, which is here, there is a happens before between collects here, it's lost here. So we can get any order. Again, the obvious way to fix it to think more carefully about natural IDs of the join result. So we have to have natural IDs which closer resemble the input sources. And here we have to add the author ID to the natural ID. So it's important through via which key we have joined the inputs. So we can issue proper inserts and updates. So to wrap it up, to solve deletes and updates, we have to keep previous element state. This kind of, when you read it, it's kind of obvious, but it might be not when you start to implement. So to delete previous value, we have to know previous value. And another thing to realize is stream elements are not business domain entities anymore. We are dealing with commands like please upsert this, please fix the state like this, please delete this value. So it's kind of mini programming language inside the data elements. And the joined streams must have natural IDs. It might be impossible in some cases where join cardinality is not set-like if you have many-to-many joins where you allow duplicate values for the left and right. But in our case, we have natural IDs, so it can be solved. So the generic way to join two streams would look something like this. We would have, with co-flat map, we have accounts and publications, and we first have to store previous value. And we store previous value for each ID in the input stream. So we have to key that stream by primary key and keep a state of previous value if it's not a delete. Then we do it the same for the second hand of the join. So we store every previous value there for each publication. And then we join by another key. So we send that data to another operator from the one side and from the other side. And when our join result is full, we just trigger the join result or maintain the join result. And we collect it again to Kafka. So this part, these three operators, even though they are different, like separate Flink operators, they are pretty coupled. And when they are communicating specific protocol of commands, do this, update this, delete this, and this can get very hard to understand. So it makes sense to have this set of operators, maybe have it in Flink, not like customly implemented outside of the Flink. Then let's see the memory requirements. Yeah, so Obviously, we have to have full copy of the account stream here to have a previous value. And we should have full copy of another stream here to, yeah, again, do a diff and route the inserts and deletes. Also, when we join, on the left side, we have, again, account stream copy. And on the right side, we have the publication stream copy. Yeah, this is pretty huge amount of memory required. Let's see what is the network load. In the input, because we read from Kafka, here is a network. And we need keyed streams. We have to reshuffle the data by key to use value state, or yeah, Flink managed state. And then to do a join, we have to again reshuffle here by different key, which is author ID. And then we have to send that data over the network to Kafka. And when we want to, so we don't treat state as source of truth. We try to treat operator state as something we can just throw away but have very fast rebuild times. And when we replay the full history, this network load can be a huge bottleneck. This is the limiting factor. And another thing is, as you have more memory, you want more machines to partition that memory across the machines. And the more machines you have, the more data is not local to a task node. So this is kind of a trade-off. Yeah, more machines, more state, but more data is in the network. And actually, theoretically, first reshuffle can be optimized away if Flink provides a way to define, to say that, yes, I want a keyed stream, and my data is pre-partitioned by key, which is the case for Kafka. If you use Kafka as change data capture, then it's already partitioned by key. So to wrap up, in addition to Kafka consumer-producer traffic, we have to reshuffle the data twice over the network, which is during the normal operation of the stream is maybe, it's not an issue, but when we have many streams, it's easy to deploy, it's easy to experiment, you are replaying stuff, it can get out of hand, and it's pretty big load. And we have to, this might be not obvious when you start to implement a join, but the reality is to join two streams, it's not enough to have one copy of the stream in memory. We have to have two copies. Yeah. And so we decided to use Flink, and this system is on production since beginning of this year. And we have millisecond latencies. I think it's a huge technical success story. And the job is up and running. I mean, we went live with snapshot versions of Flink 0.10. And we have to disable some stuff which was unreliable back then, like checkpoints. But since then, the reliability and other aspects, operational aspects, are being improved. And this is, I think, like very good and strict use case for streaming job where it backs the user-facing data. If you're interested in such problems, please visit that page. And yeah, thank you. And any questions?
Questions? Thank you for the presentation. What happens if you fail to find correct author ID in the beginning? So if you have to change the author ID of the publication, like it was incorrectly parsed in the beginning, and then it's another author, or they were joined in the beginning, but they are different people, and you have to split it in two authors.
So we will have in Kafka stream always we are tapping to the database, so we will have always the value from the database. And which means that if something happened before database, we will reflect that error. If the value in database is correct, so our input is correct, and we messed up with joins, and we have incorrect state, because of zero downtime deployments, we just fix it, replay it, and we will have replayed data in less than an hour. And when Flink is elastic, we can do it even faster.
But what if the original data from the database is incorrect? So how you can reflect it in the Flink state? And
you mean the database state is incorrect? Yeah, that would mean that we have like bigger problems. And when we fix that, like the owner of the database eventually fixes that problem, then we will have those fixes in change data capture, and it will naturally resolve the state in Flink, because when database is fixed, then we have that change in the Kafka, and the join is reflected. Does it answer your question?
I guess yes, but I guess it's more complex than everything that we covered in this presentation.
Thanks. So are there features that you would be wishing for in Flink that would have made your job or that challenge easier?
Yeah, the introspection of the state would make it easier to experiment with joins, because it can get frustrating if something fails. And yeah, the supervisor part, like operational part, is like we have our own supervision for Flink jobs in Yarn, and that part could definitely make our lives easier. Yeah.
Okay. Is there some primitive in the API that could have been more useful to you? Because it seems like you're doing a join extremely manually, like a symmetric. Sounds like a symmetric hash join to me.
Yeah. So in the newest version, I think the folding state is closer to what we want. But yeah, it would. So if we have evictors, which can be flexible enough to maintain that join result. So currently with evictors, we can just cut the tail of the window, and then we can maybe abstract comments, and then it would solve it would make things easier. And this first reshuffling could make me improve the performance.
Thanks for your presentation. I have a question related to, does the data come in order, the data change event?
In the input?
Yes.
You mean in the input?
Yeah, like from the source.
From the service, because we tap into change data capture log, it reflects the operations on the database. And we can receive that data, and so whenever some data is written to the database, we have that record moved to the tail or head of the Kafka queue. So order changes, and we don't try to rely on order. Yeah, maybe someone will decide to receive full change data capture stream, and we will have very high throughput there in the input, but order can be really different. And so because we read from two streams, we can read at different speeds, and in between, we can have different join results. But yesterday, there was a good talk about the stream equality, I think from Alibaba, and then, so for us, it also matters that if you replay full streams, materialize that view, if the end state is equal, then they are equal. So we care about the consistency when you are tailing the change data capture streams.
Okay, thank you so much. We have a break now, so see you later.
Thank you.